Okay, we're on to Chapter 5, Shape of Distribution. I just want to mention that we're continuing on with really the third part of univariate descriptive statistics for numeric variables. So in other words, one thing that we can do is summarize the typical or common variable and our measures of central tendency, the typical or the common value, and our measures of central tendency do that. So then a second thing that we do in describing data is summarize variability around central tendency, and our measures of variability give a sense of how spread out the data are. So the final notion in univariate descriptive stats for numeric data is shape of distribution. And in essence, shape of distribution is getting at the pattern of the variability, the shape of the data. And this will become clear as soon as I start to show you distributions of different shapes. But you may know the bell-shaped normal curve, perhaps from a prior course. Some other shapes that distributions might have. Some distributions appear tipped, say with most of the cases congregated perhaps on the left side, and thus the curve being very high on the left side, but then fewer cases on the right side, and so to speak, the tail of the right side very, very spread out to capture extreme values. And then some distributions are quite pointed, which in statistics is sometimes called peaked. They have a sharp mountaintop, in essence. And others are flat and broad and rounded, the opposite of peakedness, in essence, flat. The best by far known distribution in statistics is the normal distribution, also called the bell-shaped curve. Now, I do want to say as we begin discussion that no real-world variable has the exact shape of the normal distribution. The normal distribution is abstract, it's mathematical, it's a theoretical distribution. Three key characteristics are often cited in describing, or we can say defining, the normal distribution. One defining characteristic is that the mean, the mode, and the median in a normal distribution all have the very same value, and that value will be at the high point of the distribution's line or curve. A second defining characteristic for the normal distribution is that 68% of cases, approximately, are located within one standard deviation of the mean. The next slide will start to make that clear. And a third defining characteristic is that the normal distribution is symmetric, or we can say symmetrical. Its left and its right sides are mirror images of one another. Here is a slide conveying the normal distribution, also known as the bell-shaped curve. This next slide is conveying to you that the mean, the median, and the mode of the normal distribution all have the same value, and that value occurs, so to speak, right in the middle and at the high point of the frequency distribution curve. You can see that 50% of cases in a normal distribution are below the mean, median, and mode, and 50% are above, and we'll talk a little bit more about that subsequently. The normal distribution spreads out in both the positive and the negative directions. And the areas in the extremes of a distribution, that is, its far left side and its far right side, those areas are termed the tails of a distribution. So a distribution often and usually has two tails, a lower tail and an upper tail, or we can say a positive tail and a negative tail. This slide depicts the percentage of cases in selected areas of the normal distribution. Now recall that in Chapter 4 you learned how to calculate a variable, or we could say a distribution's standard deviation. So the 0 point here in the middle is right at the mean, and we can also say it's right at the mode and right at the median. So that if we go one standard deviation below and one standard deviation above, if we span that range, 68% of the cases, and indeed 68% of the area, if we're thinking visually, in a normal distribution, is within one standard deviation of the mean. So the 0 is conveying the mean. Here we are one standard deviation below, and here one standard deviation above the mean. Now a second thing that's true, and true of every normal distribution, is that about 95% of cases are within two standard deviations of the mean. So if we go down two standard deviations and up two standard deviations, 95.44 is the actual percentage. About 95% of cases are in this range. So this area that I'm sort of showing you with my cursor here, this area from -2 to +2 standard deviations comprises about 95% of the area of the normal curve. So without using formulas, let's just almost visually think through a problem. So suppose that we have 100 women, and that the mean, I guess I'm saying that we have 1,000 women, excuse me. The mean height of these 1,000 women is 66 inches, and we go ahead and we calculate the standard deviation of height, and that computes to 3 inches. And let's further say that height has a shape that is very close to normal. The distribution of height is approximately a normal distribution. These three things having been given, can we answer this question about how many women are between 63 inches and 69 inches tall? Observe that 63 inches is one standard deviation below the mean. The mean is 66. A standard deviation is 3 inches, so if we subtract one standard deviation, we subtract 3 inches, and 63 inches, therefore, is one standard deviation below the mean. And using the same logic in a positive direction, 69 inches is 3 inches above 66. It is one standard deviation above the mean. So this range from 63 to 69 is indeed a range from one standard deviation below to one standard deviation above the mean height. And therefore, we can remember the prior slide and the defining characteristic of the normal distribution, and indeed this is a percentage that perhaps you ought to burn into your brain, so to speak. 68% of the women will be between 63 inches and 69 inches in height, approximately so. And what is 68% of 1,000? 680 women. So about 680 women will be in this range. To this point, we've talked only about one distribution, that distribution being the normal distribution. Not all distributions are normal, and so we're only able to do this problem because height was defined in this situation to be a normal distribution. Okay, we're going to try to respond to a different question. What percentage of cases in a normal distribution have values greater than the mean, and for that matter less than the mean? So let's work the logic through on this. By definition, the mode, mean, and median of a normal distribution all have the same value. Thinking back to Chapter 4, one definition of the median is the score at the 50th percentile. If a score is at the 50th percentile, that's conveying that 50% of scores are higher and 50% are lower. So therefore the median is at that 50th percentile, and indeed it's 50-50 for the median. Finally, the mean and the median have the same value and these same percentages. 50% of cases are below the mean and 50% are above the mean. These same percentages apply to the mean. And we're just popping back to the prior slide to show you visually, indeed, that 50% of cases are below and 50% of cases are above the mean in a normal distribution. The normal distribution is, so to speak, the most famous distribution in statistics, but it isn't the only distribution, which again is to say that many variables have distributional shapes that are very different from normal. An important distribution is the skewed distribution. Skewness is the degree to which a distribution departs from symmetry. We're going to see that there are both positively and negatively skewed distributions. Let's first discuss positively skewed distributions. In a positively skewed distribution, cases are clustered on the lower, which is to say the negative or left side, because that's where most of the cases are. The curve is highest on the lower or left side, and that's demonstrated here by these high values. The upper tail, which is to say the right tail, in a positively skewed distribution is quite stretched out and, so to speak, elongated. Conversely, the lower tail, the left tail, is short and stubby. So, here is a look at a positively skewed distribution. And the next slide is going to show you some distributions with differing degrees of positive skew. Here are some distributions with differing degrees of positive skew, and I've attached the adjectives just with my own judgment. I don't know of a point precisely when skew changes from modest to moderate to strong to extreme. So this is to give you a general idea of a look at distributions with differing positive skew. But you can see that the modestly positive skewed distribution has a shape that departs only modestly from normal. You see just the beginning hint of a short, stubby left side tail and the large, elongated right side tail. And you know the positively skewed distribution, counterintuitively perhaps, but it tips left. So this distribution is just starting to show that leftward tilt. And you can see as we move towards greater and greater degrees of positive skew, the tail is getting progressively stubbier on the left side and elongating on the right side. Let me just mention quickly on tails, particularly tails of the normal distribution. You can't show on a slide a tail extending infinitely. But indeed, with mathematical theoretical distributions, oftentimes it's the case that the tails do extend infinitely. And that is indeed the case with the normal distribution, that the tails get lower and lower and lower, but they do extend infinitely in both directions. Well, let's see if you can kind of reason out intuitively why family income in the United States is positively skewed. And of course, this data here is hypothetical, but the curve for family income is quite high on the left side, the negative side. And this is conveying that most families in the United States have moderate or even low incomes. So that this graph is depicting most incomes as being less than 100,000. On the other hand, income stretches out a long, long way in the positive direction. So that's where we get our elongated positive tail. And I mean, this graph is only going out to 1 million, but clearly there would be some families who would be making even $1 billion or more per year. So the left side tail is very compact, and really, I mean, if we, depending on how we would define family income, if we define the lowest income possible to be 0, well then, really there is no left side tail, and so it's then therefore as stubby as it could possibly be, and obviously, as just discussed, the right tail is elongated in the positively skewed distribution. So I guess with the negatively skewed distribution, what we're doing is just flipping our perspective 180 degrees. Things are just the opposite as compared with the positively skewed distribution, so that the cases are clustered on the positive side, and therefore the curve is higher on this side, the right side. So in the negatively skewed distribution, it is the left tail, the negative tail, that is elongated, and it is the upper tail, the positive tail, that is short and stubby. And the next slide will show us some distributions with differing degrees of negative skew. And here is that slide. And so you can see that we're moving from modest to moderate to strong to a distribution that has extreme negative skew. And here's the example from the text to just sort of help you intuit out the negatively skewed distribution and why it is that way. So what we're depicting here is length of gestational period for newborns. And for purposes of discussion, we're going to make this length of gestation for newborns who survive childbirth. What's the mode of the distribution, the high point of the distribution? Well, the high point of the distribution is somewhere pretty darn close to 9 months. And the mean is probably close to 9 months. I suppose the mean is a little bit in this direction. You can see clearly that this distribution is tipped to the right. I mean, and so that's what a negatively distribution looks like. It tips in the positive direction. And I mean, the defining characteristic is the extending tail, and it's the negative tail that is elongated, and so that makes this a negatively skewed distribution. The positive tail is stubby. So why is the positive tail so stubby? Well, picture childbirth. Let's say in Oklahoma, the state where I am now. There just simply are no children delivered much beyond 10 months. I mean, when you would get to 10 months, it's my experience, and I have not much experience in this, but a C-section or other inducement of labor is going to come there. So we just don't have much extension of the tail. It's very tightly compacted on the positive side. But on the other hand, as you all know, particularly with advances in medicine, some kids are born at 7 months, and some even survive at 6 months or 5, and the tail goes on farther. I don't know the exact reach of medical science at this point, but the idea is that even though the numbers are fairly small, some children are being born at times that differ greatly from 9 months, and that extends our tail in the negative distribution. So therefore, hope it makes some intuitive sense to you that length of gestation is a negatively skewed distribution. I'll just sneak in the point that in actual research practice, you will more commonly encounter positively skewed distributions than negatively skewed ones. Here's the mnemonic from the text. A student thought of this. So, if you're tested, is this a positively or a negatively skewed distribution? Remember, the tail tells the tail. It is the elongated tail that is connected with the distribution's shape. For instance, in the positively skewed distribution, the positive tail is the elongated one. What are the implications of skewness for statistics? And right now we're dealing with univariate descriptive statistics. Skewness can exert influence on measures of central tendency. That's particularly so for the mean. In a positively skewed distribution, indeed saying that a distribution is positively skewed says very much the same thing as saying outliers are in the positive tail. It's the positive tail that elongates. That's where the outliers are located. So if that positive tail stretches out far enough, and indeed as it stretches farther and farther, the values there become increasingly extreme. So if you have a sufficient number, and you don't need many if you have small sample size, if you've got outliers way out there in the positive tail, when you go ahead and compute the mean, it's going to pull the mean upwards. And negatively skewed distribution, well, to say that that's the shape of a distribution says much the same thing as to say the outliers are predominantly in the negative tail. And the very, very low values have the effect of pulling the mean downward. So what you want the mean to do is to convey to you the common and typical everyday middle value. If a distribution is sufficiently skewed, it can be so skewed that the mean becomes a misleading measure of central tendency. And by a misleading measure, I'm meaning, for instance, with family income, typical family incomes, middle family incomes in the United States, if indeed there even are middle incomes, because that positive tail is so skewed out, one could say, well, there are no middle incomes. But middle and common incomes tend to be on the left side of the distribution, and more often below the $100,000 mark, so that the very few, very high incomes of individuals, the outliers, could pull that mean so far above the, quote, common typical, that the mean would be misleading. That someone would look at the mean and say, aha, the typical family income is such and such, whereas in reality, the common, middle, more typical income would be substantially lower. So I'll just go on and say, when you have enough skew, median is generally preferred to the mean. I'm not sure I can give you a precise definition of when a distribution becomes so skewed that the median is preferred. But I would say perhaps for strongly and extremely skewed distributions, as we showed in the recent slides, the median is perhaps preferable. And I mean, I've already discussed this point here. Very strong skew and the presence of outliers in one tail. I mean, those two situations are basically one and the same, and indeed the outliers are in the elongated tail. If these lines weren't labeled, could you figure out which one conveyed the mode, the median, and the mean? And I'll go ahead and work that through with you and for you. So the mode is the most frequently occurring value, the most common value. So the high point of a curve, that's always the mode. So the mode of our positively skewed distribution is at the high point of the curve. Now, values in the tail pull the mean in the direction of that elongated tail. So the line that is closest to the elongated tail, that's going to convey the value of the mean. So this line is the mean. And by process of elimination, the middle of the three lines is the median. In a negatively skewed distribution, the extreme values in the lower tail pull the mean in the direction of the tail. They pull the mean downwards. So the leftmost line in the negatively skewed distribution is our mean. And as always, the mode is located at the most frequently occurring value. So here's our line conveying the mode. And finally, the median is the line in the middle. This slide is for the most part just capturing what we went through in talking about the prior one. So I'll just let you read for a few seconds. And then I'll mention that in the normal distribution, mode, median, and mean have the same values. In skewed distributions, I mean almost without exception, these three measures of central tendency are going to have different values. We've discussed skewness, another characteristic that researchers look at as they assess distributional shape is kurtosis. And kurtosis can be defined as the degree of peakedness, or I could even say the degree of pointedness of a distribution. So a distribution with a soaring mountaintop peak, narrow and pointed, is going to have high kurtosis, and on the other hand, broad, flat kinds of distribution have low kurtosis. So again, high kurtosis has a peaked shape, and you know, it is the case that with high kurtosis, you also have big, thick, elongated tails. So it's like you have very big and very, in a sense, pointed tails and a very sharp point in the middle. And your distributions with low kurtosis have flat, broad shape and stubby tails. So here are three distributions with differing degrees of kurtosis. Here's a distribution with high kurtosis, and you can see both the elongated tails and the pointed high center of the distribution. The normal distribution is considered to have medium kurtosis, so it's our example of a distribution with medium kurtosis. And here is a distribution with flat kurtosis, and it's characterized by a flat, broad shape and short, stubby, small tails. At the risk of oversimplifying, let me just say that on balance, and particularly for introductory statistics, a distribution's kurtosis has a less import for what statistics may and may not be used than does a distribution's skewness, which tends to be more often more important in this area. This slide depicts a distribution with a uniform shape, or sometimes the term rectangular shape is used. If a distribution was perfectly uniform, then the height of each of these bars would be the same, conveying the exact same frequency for each value. Final distribution that I'll mention is a bimodal distribution. So a bimodal distribution, so to speak, has two clusterings of values, so to speak, two central tendencies. So now perhaps heights of women and men would follow a bimodal distribution. There might be one peak for where women's heights cluster, and a higher peak, which is to say one more to the right, one more in a positive direction for where men's heights tend to cluster. Well, we're going to go back and talk some more about the normal distribution. Keep trying to build on some concepts that are connected with it. Recall that in a normal distribution, 68% of cases are within one standard deviation of the mean. And this is taking into account cases in both directions. Now, what percentage of cases in a normal distribution are between the mean and one standard deviation above the mean? How do we answer that question? The normal distribution is symmetrical. So we know that 68% of cases are within one SD, both directions considered. If we're only considering the positive direction, that is, cases above the mean, it must be the case that the percentage is 1/2 of 68. So dividing 68% by 2 tells us that about 34% of cases in a normal distribution are between the mean and one standard deviation above the mean. Let's go ahead and use the next slide to do some more percentage problems for the normal distribution. Well, we just did this problem. We just figured out the percentage of cases between the mean and one standard deviation above the mean. What about between the mean and one standard deviation below the mean? Well, we'd use the exact same logic. Our distribution is symmetric, so it's the same percentage, the same 34%, 1/2 of 68%. Let's think about cases within two standard deviations of the mean. So recall that about 95% of cases are within two standard deviations of the mean. What percentage of cases are between the mean and two standard deviations above the mean? We would simply divide 95%, it's actually 95.44% by 2, and so then therefore 47.72% of cases are between the mean and two standard deviations above the mean. And similarly, 47.72% are located between the mean and two standard deviations below. Do take a look at this figure to see, that virtually all cases in a normal distribution are located within three standard deviations of the mean. The actual percentage is 99.74, and we divide by 2, and so, for instance, 49.87% of cases are between the mean and three standard deviations below the mean. And indeed, the tails of the normal distribution extend infinitely in both directions, and we can't really convey that with a figure. This slide simply works through some of the problems that we just talked through, so I'll just leave it on for 5 seconds or so you can take a peek and see what you think. See how the problems work. Well, the kinds of problems that we've been doing so far have had to do with cases that are within some given standard deviation range of the mean. But we can do the opposite kind of problems also, which is to figure out the percentages of cases that are more than some standard deviation amount above the mean. So for instance, what percentage of cases in a normal distribution are more than one standard deviation above the mean? What's the logic for working out the solution to this question? You know by definition that 50% of cases are above the mean. Prior slide, as well as our computations, demonstrated that 34.13% of cases are between the mean and one standard deviation above. So what we need to do is take 50%, the total percentage above the mean, and subtract out the 34.13% to yield 15.87%, and that is the percentage of cases, and indeed the area of the normal curve, that is located more than one standard deviation above the mean. Let's shift our perspective back to both directions again. What percentage of cases are located more than one standard deviation from the mean, both directions considered? So there are two ways you could carry out this problem. One is that we just calculated that 15.87% of cases are located more than one standard deviation above the mean. If we want the percentage of cases that differ from the mean by one standard deviation or more, both directions considered, the normal curve is symmetric, so we simply double our 15.87% and conclude that 31.74% of cases are located more than one standard deviation from the mean in a normal distribution, both directions considered. And a second way to do this problem would simply be to use one of the earlier normal distribution figures that we looked at. So let's go ahead and take a look at it. So here are some calculations at the bottom of this slide. What percentage of cases are more than one standard deviation away from the mean? Well, obviously there are 100% of cases in the normal distribution if we capture all cases, and we know that 68.26 are within one standard deviation. So we've got to subtract out that 68.26 and we get our 31.74% more than one standard deviation away from the mean, both directions considered. And here, for instance, is the calculation for cases more than two standard deviations away, both directions considered. We subtract out the 95.44% and we get about 4.5%. Well, we've done some work on central tendency, on variability, and now on shape of distribution. Let's just quickly put that work together in an example. So suppose that you read that the mean birth weight is 100 ounces, the standard deviation is 12 ounces, the shape of the distribution of birth weights is close to normal. So how can you work with this data in your mind to help your mind summarize the information? Well, you know that about 68% of babies weigh between 100 ounces minus 12 ounces, that being the standard deviation, and 100 ounces plus 12 ounces. Therefore, about 68% of the babies are between 88 and 112 ounces. Clearly, 68% is very close to 2/3. So you might say to yourself, about 2/3 of babies weigh between 88 and 112 ounces. So you're interpreting this univariate data. I don't have a slide that does so, but perhaps your mind can picture the high point of the curve centered at the mean of 100, and then you'd go away one standard deviation in each direction, and that's the 88 to 112, and about 2/3 of the kids are in that birth weight range. And you'd picture the normal shape too. We've not got in particular skew, so perhaps this distribution, as it's close to normal in shape, it's got a bell-shaped curve to it, and maybe your mind can picture it. Chapter 5 is a long chapter, and I think what we're going to do here is wrap up this video, which is in essence kind of going over the first half and a little bit more than that of Chapter 5, and we'll go after z-scores in the next video.